Hello everyone and welcome to another SAT physics video. Today we'll be talking about magnetism and we will be solving together some magnetism exercises. So the first exercise, a wire carries a current out of the page. Which diagram below correctly describes the magnetic field of the wire? So here we have to know the right hand rule, which indicates that the current is counterclockwise, which is answer D. Alright. The second question is, a wire carries a current I, that the distance of R, the magnitude of the magnetic field is B. If both the current and the wire is the distance, and the distance from the wire are doubled, the magnitude is, okay, so in this case we have to know this formula. Alright, and if it's double, if both of them are doubled, then this one isn't changed, so it's C. The next question, which of the following fields cannot change the speed of the object that is acted upon by each field? So we know that gravity and electric field can speed up objects and slow them down when objects are moving parallel to these fields. But the uniform magnetic field can cause objects to circle at constant speed. So the answer will be C here. Alright, now exercise 4. What is, okay, let's read this one. Negative charge Q is moving with this here. Speed V in the plus x direction enters the uniform plus x magnetic field B as shown in the diagram below. What is the direction of the force of magnetism acting on the charge at the instant it first enters the magnetic field? Alright, so here we have to know the left hand rule, which indicates that is plus y, so it's B. Let's go to the next exercise. How is the magnitude of the force of magnetism acting on the charge affected by doubling the magnetic field? So we know this formula, and if this one is double, so affected by magnetic field, so it will be like that, and the answer will be D. Now let's go to the next exercise. A rectangular loop of wire is moving How is the acceleration of the charge affected by doubling its initial velocity? So we know that in this case, let's go back. Wait a second. So we know that the magnetic field looks like this, and it's circular. So this force is going towards the magnetic field, so it's centripetal because it goes to the centripetal force. So here we will just use this one. We will make these two forces equal and then write their formulas and just solve it. So then the centripetal acceleration will be equal to this one. Alright. But if it doubles, then doubling the velocity doubles the acceleration. Here I forgot velocity. Yes. And doubling here would also double here, so 2 times larger. It's D. In the diagram above, a loop of conducting material is placed into a uniform external magnetic field. A current runs clockwise through the loop, blah 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 blah, in the minus x direction. So here we have to use the right hand rule. Straight finger version, so it will be B, away from the center of the loop, and X to expand the loop. Alright, now let's go to the next one. 2 parallel wires carry current in the same direction as on the diagram above. One wire carries 2 ampere current as seen here, and the other one carries 1 ampere current. The force of magnetism acting on 1 ampere wire is... So, we know that 2 parallel wires with current in the same direction will attract one another. However, the key to this problem is actually Newton's third law, which is that when 2 objects interact, there is an equal and opposite force between them. So, the only answer involving equal force is E. The 2 different currents act as distractors. So, the same as the force acting on 2A wire, and the wires attract. Alright. Now, that's it, actually. Oh, no, there were some more exercises here. Which statements is not correct for the motion shown in the diagram? So let's read each one of them. During the entire motion, the magnetic flux is constant. So let's think, what is the magnetic flux? So we know that magnetic flux is the intersection of the magnetic field and the area of the loop. So here is the magnetic field, this one, maybe like this. No, sorry. Yeah, like this. And here is no intersection, and here is intersection. So the magnetic flux goes from 0 to maximum, because here is absolute maximum. Yeah. So this one is false, because the magnetic flux is not constant. Alright, let's go to the last one. During the interval where a current is induced, its magnitude is. So we know this formula. Oh, why isn't it writing? Okay. We know this formula. Alright. And then results that I equals to this. But we also know this formula, so we will just replace them and have this final formula. So here is just a game of formulas. Where is this option? It's B. So that was it. All you have to do is revise and do together some exercises. Thanks a lot for watching, and do not forget to subscribe for more videos like this.